Yes, please.
Yes,
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 please.
we
yes,
can.
please. Right. So my name is Michael Kofi. Um, yeah, I'm a machine learning specialist at Haptel currently. So I specifically build machine learning and AI models, of course, in order to make the application better than it is. Um, to be more specific, what I deal with is transactions and the security around them. So you can associate it to transaction integrity, being that everything related to what comes in and out of Haptel related to money. If there is some form of, compromise around that part, then we have to find a way, or I and my team have to find a way of building ML models or AI models to mitigate it. So use cases like fraud detection, anomaly detection, or predicting what we are supposed to earn in terms of money in the coming future, are machine learning use cases. And these, because they are related to transactions, are within my domain. So that's basically what I work on. It's a pleasure meeting you all. I see most of you are from UMass, which is quite good. All right, then. Can I get a response? Right. Okay, so let me share my screen and see what we can achieve today. I'd want the class to be very interactive as possible and exciting, right? For today, I think because it's the first time, we are basically going to look at the very start of everything, right? A little history, a little background about what we are doing here is what's important to us.
Is the TA that's named as
Try and mute yourself. All right. Let me know if you can see my screen.
Yes, we can see it.
We can see your screen, please.
All right, then. That's good. Okay, so now that you've seen my face, I think it's better that I take the video off just so I don't scare you and take your attention off, right? Is that okay?
Yeah, Michael, go ahead.
Yes.
Go ahead. Yeah.
All right, then. Give me a second. Yeah. Right. So what are we achieving in the first place? Machine learning. Okay, the big term. Now, when we talk of machine learning, it's a broad thing that has a lot of things under it. Okay. But machine learning itself is coming from what you all know as artificial intelligence. All right. So just to make sure this becomes very playful and interactive as possible, there is this very exciting presentation of PDF that I found from University of Stanford. And I think it's very nice that we all go through it together to understand the concepts we are dealing with. So what is machine learning? Now, imagine we take an example, okay? This as an example. If I ask anybody here what this object is, I'm sure that you'll be able to tell me that, hey, this is looking like an image of a car, okay? So obviously it's a car. So that's what you're going to tell me. Now, lots of things are objects like, so you might think of different types of vehicles, okay? So you might think of a bike, you might think of other types of car, but to be more specific, you describe it as a car, and you even be able to tell me that it's a red car with tires underneath and whatnot. Now, I believe most of us have watched the Tarzan movie before. So imagine you asking Tarzan, who has lived in the forest for so many years without any education, that, hey, what is this? All right. You can liken Tarzan, if you've not watched it before, to more like a baby. A baby doesn't know anything that much, right? So you asking all those questions like, what is this? A baby will not be able to answer you, or even a 2-year-old child that has started learning without doing this from school will not be able to answer you. So, of course, it's not able to recognize it. Now, you can tell from the image here that this is what it's thinking. So it's comparing lots of things. It's thinking of giraffes, elephants, uh, tigers, lions, whatnot. But you showed it this very object, and you're expecting an answer to be right. But he's human, right? Of course, he's human. And for every human being, we can observe, sorry, and then learn. And so how do you make Tarzan to recognize different objects that you show him? So you show him this, he isn't able to learn, but then now, so because we want him to understand what this is and then make, or give the right answer the next time, what we do is that we show him this again, and then we tell him that Tarzan, this is a car, okay? So we show him this so many times, he gets accustomed to it. Then next time you go and ask, out of all the things that I know, which is elephant, tires, and now car that you showed me, I think this is closer to being a car. Okay, that is for the human aspect. Exactly. So that's how human beings do learn, of course. So it's the same way. When you are in a classroom, you know nothing about any concept until your teacher tells you that this is what it is. Okay. So there is this saying that you know not what you don't know. So if you don't know something, sometimes you don't even know that it exists until somebody brings it to your realization. That's the whole concept around it. Now, that is how human beings learn. And this example depicts the way or methods that, of course, human beings do learn. And it's quite simple and intuitive. But what about machines? What about machines? This is where it gets a bit tricky. So most of you coming from computer science, I believe that you understand around that machines or computers are built. It's the very basic foundation is zeros and ones. And how do you make zeros and ones meaningful? Okay, now we have so many advancements out there that is very easy. Most of us use this type of systems without knowing that very huge computations are running behind them. Okay, but a very basic machine doesn't even know what a car is when you show it an image, just like Tarzan. Okay, machines cannot make decisions on their own. But then some things have been made possible in our current stage. From when it started in the 90s to now, we know that addition is possible, right? Multiplication is possible. Division is possible with machines. We can do comparisons, we can even plot graphs, we can print stuffs. You understand? Is somebody asking a question? Thought I heard something. Okay. So we can do all this with a machine. But how do we make a machine act like a human being? Right? How do we make a machine act like a human being? So that is one big thing. In this sense, what we want to achieve on the first round, just like what we did to Tarzan, is to make the machine to identify these objects that we have here. So we show this object to the machine and expect it to identify this object. Or we can also show this object to the machine and expect it to tell us the price in 2025, hilariously, imagine. Or we can also say that we have a machine and then we want the machine to correct mistakes in our writings and whatnot. I've mentioned 3 things so far, and if you can relate, you realize that in our current age, all these things are possible. Especially with this correction, you have things like ChatGPT that is able to, you can send in a prompt, or you can basically query something like, I have this test or this statement, now correct the mistakes in it, and it's able to do so, right? We can also let it recognize faces in images where possible. So in order to achieve this, we need to provide what experience to the machine for it to learn like the way we made Tarzan to learn, of course. So we need what we call as data, the very basic foundation. Now, this is where it gets interesting. Similar to the way we made Tarzan learn, that image of a car that we showed to Tarzan is also an example of data. Data is basically the ground of everything. You understand? So you show data to Tarzan once, twice, or 3 times, as many times as possible, just so that next time, if you go and then you show that data to the same Tarzan again, because you showed it that data before in the past, it's able to recognize. We do the same with machines as well. So we have different types of things that we want the machine to understand, or different types of objects that we want the machine to understand. Okay, that is what we call as data. And that is what in typical machine learning jargon, we training data. All right, try and mute yourself. Miss Noble here with me.
Yeah, Michael, go ahead. I'm looking at it. I'm checking it. I will mute the person. Sorry about that.
All right, sure. Okay. All right, then let's continue. So that is basically what we call as training data. Okay. And it's the very first foundation of how we tell a machine what is something. So you pass the data to it, then you expect that it goes through different processing or different stages before the machine can learn. Now, with human beings, we didn't go through some cycles to understand how to make a human being get something. Why didn't we do that? Because intuitively, all of us understand how, or the measures we take in our mind to learn, okay? And most of us even don't know how it goes about, but it's a miracle. I think I'll leave that to the science part of it. But anything can be achieved human-wise in a very easy process. And that process, computer science or in computing, we tend to mimic that behavior for computers to understand or to learn also. And so when we talk of data, we say that anything that you feed to the machine learns exactly as is and then produces to you exactly as is when it is asked next time. And so it means that if you feed in garbage, and garbage is going to come out. It's a simple rule, garbage in, garbage out. So the training data now has to go through a series of processes for it to be very fine or in the right shape that it's supposed to be. Okay. So now with the training data inside our data set, okay, then we need to get processes to process the data or algorithms to even learn on the data. So we have a series of things that we call as algorithms. Okay, now I said things, but they are not. Let's go a bit technical and use the right words. We have different approaches of making computers learn, right? Now, these approaches, most of them are mathematical wise. Some of them to what I'll call as rule wise, all right? Now, mathematical wise, we have statistical approaches, of course, and we have ones that people compute and then bring out those solutions as though they are type of math that will let a computer remember some form of activity. You understand? So that is what we call as algorithm. All these ones are algorithms. So if you hear me talk about algorithms, just as it's written here, that we devise algorithms and execute programs on the data, those things or these jargon that we call as algorithms are basically mathematical approaches or rule-based approaches that we put data into just so that next time when we ask the right question or the questions that we know that we've trained them on, they are supposed to give us the right answer. Right, so using these programs, of course, with the data in our hand and with the algorithm also, we are able to identify the patterns or the rules to apply. You get it? And I'm going to give you a typical scenario. I know we've all done some form of programming, right? So in a typical code, you have rules in there where you already know the rule to something.
Michael,
Yeah.
check your DM, man.
All right. Yeah, give me. Yeah, sure. Let's go ahead. So in a typical,
Go ahead. Yeah.
because I heard most of you say computer science, so and this program or this tutorial
okay.
that you have.
Michael, focus on that. Focus on that. Don't change that. You focus on that. You go ahead. Yeah.
Okay. All right. So the assumption is that you all have very good experience with programming already. So in your typical code, when you're writing your if-else statement, of course, you do have the rules at hand. So anything that you are trying to build a software on, you know the approach to take. So you know the rules already. And so you write if this, then that, and what's not before you get your function to return what you're supposed to return. Now, it becomes a bit different for machine learning because then we don't know the rules at hand. This is where it becomes an advantage, okay? In settings where we don't know the rules, the opposite of the former. So if we don't know the rules, then it means that we need to get an algorithm, set of mathematical instructions, okay, that will be able to tell us what the rules are. And how do we get the rules? In order to get the rules, we need to get some data to show this very algorithm, right? Before it looks at the data, understands the patterns in the data, before it tells us that this is the rule that you are supposed to apply anytime you want to get something out of this. This is machine learning in a nutshell. Taking it again, for a typical code, a typical software, whatever you are trying to implement, okay, you need rules in order to achieve that. So if you've done something like data structures and algorithms before, you realize an algorithm called binary search. Imagine, in order for you to achieve this, there is already a rule that you have to follow. First, of course, they said that the algorithm assumes that the data is sorted. So it means that it has to be sorted. Second, it means that you need to get 2 pointers to be able to iterate or divide the array that you have and what's not. All these are rules that we know beforehand, or we look at the problem and then we're able to devise all these rules. You understand? But here, no, we don't know the rules. But then we have data, we have the output. All right, we have lots of output. We have things that have occurred before, but then we don't know how they occurred or what is causing them to occur, the rules behind them. And so we get this algorithm and we say that this is the data. These are a set of outputs that I have seen, right? With this output, look at it and then tell me what the rules are.
Right.
Exactly. So your output basically rules. That's machine learning.
Machine learning.
Look at your data sets and extract the required patterns. Okay, so your patterns are what we call as a model. Okay, a model is basically an algorithm that has learned on a specific type of data and identified the required patterns in it, and then it's able to be used for what inference or to be used for whatever you are supposed to be, you are trying to model. Okay, exactly. True. I've presented a law that covers all these things. So in summary, right, we have what do you call it, data. Okay, or we have a machine. Let's start from a machine. We have a machine. The machine doesn't know much. All right. And so we want the machine to be able to tell us what something is. Taking a use case. We have a machine that is not capable of telling us what in the picture looks like. So assuming you tell the machine to identify me, it's not able to do that. How do we make the machine identify me? First, you need to get images of me, or you need to get anything that describes me. It can be anything. It can be data. Data comes in lots of forms. Now you show the machine data that describes me. Now you go through processes to make sure the data doesn't have garbage. And data has garbage if it doesn't necessarily describe the intent or the purpose with which you are training the machine on. That is basically it. You understand? So all data are clean, all data are not clean. Now it depends on the use case. So let me put it that way. That's why I had to go specifically into what garbage is. If the data is well to do with the use case that you are using it for, then the data is clean enough for the model, because what you put in it is exactly what you get at the output. Put in garbage or put in anything that is not clean, and then you will not get what you expect. If you don't get what you expect, it means that when you ask the question, Tarzan in this case, that what is this object, it's not able to, it's not going to be able to tell you it's a car. It might tell you that it's a donkey because it looks like all of them have 4 legs. So that's exactly how it works. You understand? Right. Now, let's look at the paradigms. Very famous paradigms. Specific to machine learning, okay, we have 3 concepts that are very paramount. I think we've done this real quick. That's good. Now, the first is supervised. The second is unsupervised. The third is reinforcement. So we've looked at how they learn. Now let's look at what they learn. Okay. Now, that is where these ones come into play. So when we talk of supervised learning, now this is how the learning process is for supervised learning. Supervised is actually literally means the same meaning as you understand what a supervised is. It means that you need to get a set of outputs and their related inputs, okay? Then you show it to a model, or that output and related input, you can basically call it as history, all right? So imagine if you want to model 1 + 1 is equal to 3. And so 1 plus 2 is equal to 3. So 1 and then 2 are basically your input, and then you know the output already to be 3. Okay, now this is data. Now your inputs data here, what you would basically call as features, your 1 and then your 2. What you are trying to predict is 3, but in this case, you know forefront what the answer is. So 3 is now your history, right? Even though you're trying to predict, but then in this case, because you have it as training data, it's your history. That takes me a bit further into describing what training data is. Training data is basically what we know already. So look at this image. With this one, you can tell me that this is a car. This, you can also tell me that this is a car. This, you can tell me it's a bike. This is also a bike. How do we know that? Because we know this already, right? We know this, we know it. So this is the input, this is the associated output. This is the input, this is the associated output, and what's not. So if we know it already, and then we are about to tell the model that this is what I've seen, then it becomes training data. Okay, it already exists, right? Now, how does supervised learning work? So given the label data set, the task is basically to devise a function. So everything is literally a function. Everything is literally a function that takes the data set and then a new sample and then produces an output value. That is supervised learning for you. So it takes the input data and the associated output that is from history, and then it learns the patterns in it. So it learns that, okay, this image has been labeled as a car. This image, which is not even red, right? Sorry about that. All right, give me some time. Okay. So this image, which is also a car, but it's not to be a car. It seems to be an image that has red and then brown in it. And then sorry.
I'm coming. Let me look at it. I don't know who is doing that. Okay, Michael.
All right. Right. So you give it this image too, which is it's having blue color. And if you look at the image, this is moving forward, this is moving backwards. I'm pointing out to these very features because it's the very foundation of lots of things. Okay. And this has also been labeled as bike. Right. You get to easily understand it because you are human and you've probably learned before, but clear your mind. Imagine you are given something like this. So most of the time, I think what we do say is that when teachers come to classroom, they'll give you 1 + 1 is equal to 2, give you 2 + 2 is equal to 4. But when you get to exam, they give you 200 plus 3,000 plus yx is equal to what value? Then you are stuck. Exactly. So in this case, how do you think you would have been able to answer math related to all those big values? By getting examples or being able to solve questions that are at that high level. It's the same thing. So if we had fed this as training data, or if our data had just contained red cars, it would probably understand that a car is basically anything that is red and has wheels and red. But look at in here, we feed it or we feed it this object that has the color red and the wheels are beneath it is black. There is nothing in it that shows that there is anything silver in it, right? Then we come again and we feel it's something like this. It's blue. But then there is some similarity between this and this. And the qualities are that both of them have wheels under. And even though the colors are not the same and the shape, of course, is not the same, but it looks like because they have wheels under and then their way of, looking are similar, they are all labeled as car. And that is exactly what our function here needs. Our function here is basically the algorithm. Okay, or that is exactly what the model needs. All it needs to do is to be able to be directed on what exactly something is. You understand? And so that becomes our training data set. So once training data set gets in it, it learns in various ways, right? It's basically math in there. We'll get into it when we are doing the practical aspect. But the function basically has what we call as algorithms. So they are algorithms, of course. So it's basically math in there. Or sometimes some of them too are based approaches. And it's just learns from the patterns that are in the training data. Okay. And all these patterns are made or are passed through the model, and the model later on understands that, okay, so if this and this are car and this are bike, then next time when I see this, what is it? That's basically it. So you understand that there is no yellow here, but then this has wheels under it. You understand? And even in this image, it doesn't have 4 wheels. We only see 2, but then the shape and everything. So what are we looking at then? Between a bike and a car, what does this resemble? Then the model will tell you that it's also a car. This is how models learn. And this is machine learning, the supervised approach. You get it? Now, we've talked about whether it's a car or it's not a car, it's a bike or it's not a bike. And the supervised learning, we also have different ways of, achieving a supervised learning approach. Okay. What I'm giving you is essentially an introduction. So you just need to follow through and understand the concepts. We'll realize all this when we move forward. But if anyone has questions, please do unmute and then chip in and ask. Right? Exactly. So still on supervised learning, we've done a very simple part of it that was supposed to make you understand, and that is to ask a question of whether this object is a car or is this object a bike. So we give it this object and then we basically ask the function, so what is this? And then it tells us it's a car. Now in such situations, we call this type of model, this type of supervised model, a classification model. You understand? So classification it's very simple. So what it is essentially is trying to tell us distinct values. So it's trying to predict, or I don't want to use the word predict, that's why I held up over there, but it's trying to, make the function tell us something that is within a specified range. It doesn't go beyond the range that is given. Okay, so if you've done a little bit of statistics, we do have categorical values, numerical values, and of course, we have something called as quantitative analysis, qualitative analysis. When you are doing all this type of analysis, and statistics is very important here, so it's good that we mentioned that as when you're doing all this type of analysis, there is very specific type of data that you pay attention to. So if you're doing quantitative analysis, then you know that you have to deal with numerical values. If you are dealing with numerical values, you should expect values that are in a very large range or unpredictable range. So that is when you can look at 0 to infinity. So 0 and even its decimal intervals to infinity. So you can take on any value at all. You understand? Consider an example like data coming from a sensor. Obviously, it will be numerical. So for every second, or every microsecond, you get a recording. Okay, time itself is numerical. So if you want to understand clearly, time itself is also quantitative. Yeah, because every second counts. Exactly. But for classification, it deals with qualitative data or distinct data. So giving an example like, what are we dealing with? Let's get a perfect example where you have a set of numbers to choose from. Okay, so if we give you an example like on a scale of 1 to 10, then you know your boundaries. You know that it starts from 1 and then it ends at 10.
No, porque
Now,
ahora
boundaries, when these boundaries are given, the values in there do not exceed what is given. So it cannot go to 11, it cannot go to 12, or it can't go to 100. So if you're given to choose a range between 1 and 10, then you know that it starts from 1 and it ends at 10. This is distinct. And this is where we apply categories, our classification specifically to. So in this case, we know that we are only dealing with a car and a bike. You understand? So we are only dealing with a car and a bike and nothing else. And our model is supposed to choose from these two options and nothing else. You get it? So whatever we give it is basically supposed to choose from these two options. The question is, in this case, it's binary. So the question is it a car or is it a bike? Right? And then it will make a decision. So it will basically compare with what it has learned, the closest to what looks like a car. So we didn't fit it anything like a bus. See that it's very different here. But then looking at what we fed it initially, that is this car, and then this guy, and then this and this. This looks more like it's of this kind than it is to this kind. And then it's able to tell us to what degree this one looks like this, and then to what degree this looks like this. Degree I'm using here is basically probabilities, and we'll get to that. So that is what classification is all about, right? That's what classification is all about. So you feed it your data set. Another example here. Another example. You feed it your data set. Your data set in this case is an elephant, right? So we have elephants here, and then we have tiger or tigers. Now, the range is very definite or is distinct, right? The range is very definite in the sense that we only have two things we are dealing with here, okay? Elephant and tiger and nothing else. So we are not looking at anything else. It's not going to perform any superpowers here. Mind you, be very focused. I would want you to forget LLMs as much as possible to understand this. If we give it an elephant and a tiger, it's only supposed to tell us what an object is if we feed it an object that is likened to what we train with. Let me spoil something for you. Imagine if you train this thing with an elephant and a tiger, right? And then you feed a car here. What do you think you obviously expect? Anyone can unmute and then tell me what they think. But let me explain this image just so you don't understand what is going on in this image. In this image, right, there is an elephant in the training data or in the data set. There is also a tiger in the data set. Now we use this to train what we call as a classifier. A classifier is any supervised machine learning model that is learned based on the classification approach or that learns based on the classification approach. So if it's learning based on the classification approach, meaning that it's able to tell you, either predict something in distinct values. Is it 1 or is it 2? Is it 0 or is it 1? Is it yes or is it no? All these are classifications. Good example is a yes or no. There can be nothing other than yes or no. So when the person fed this image to it, the question now that we are asking is for it to identify this animal. And so it looks at these two, and then it asks basically one important question. What does this image, out of all what I've learned, right? So this image compared to this and then compared to this, what does it mostly look like? Of course, by your intuition, you won't say that it looks like that. You would rather say that it looks like elephant, even though we have just one here and then we have a lot here. This looks like it's one of these. And so the output that came out from the classifier or the algorithm or the model here is that it's an elephant, right? And that is how classification works. So then back to my question, what I'm asking is that, imagine we have elephant and then tiger in the data set. And now what we use to train the model, of course, is these two classes, right? But then we get a car here, and then we asked, we asked a question. We still go ahead to ask, identify the animal. What do you think is going to happen? I need suggestions. I just don't. There is nothing right or wrong here. Trust me. Everyone will get it right.
Hello.
What happened?
It could give an uncertainty.
Hello.
Yeah, go ahead. One after the other.
We cannot identify the object because in the train data there is no car in it, so we cannot identify that object.
Hello.
Mhm.
So
Yeah, go ahead.
it will either classify it as a tiger or as an elephant. So it will still classify it as one of these, depending on maybe the size or any category, any variable. Yes, that's
Or I think it would classify. It
Right.
will give. It will give an uncertainty.
I believe that it will look for an object in the data set that is closely or similar to the
Come in.
object we want to
Sure.
identify.
Are you there? Anyone
Yeah,
else?
so after seeing that it is close to that object, it will pick that one since it is similar to what we want to identify.
Okay, so it will still predict. That's what you're saying.
Yes, yes, please.
And what would the prediction be?
Okay. It will choose the class from the data set that is similar to that of the one we want to predict.
Hmm. Okay. Does anyone want to add something? All right, then. That is amazing. So it means you are following, right? Exactly. So even though we don't have a car in the data set, so we don't have a car here, we don't have a car here, we only have two values. So we have an elephant and then we have a tiger. But then we feed a car to it. So it's confusing. Now, the model is still going to make a prediction. Don't even bother to understand what is going to come out of the model. It can be anything, right? But we can still dig deep and then put our minds to what will come out of the model, though it's possible. And the reason is that, just like some of you said, it's very true. It will look at this elephant, oh sorry, this car that we give it, and then compare to the elephant and the tiger, which one looks like a car more? That's what it's doing. That's what it's going to do. So between the elephant and the tiger, which one looks like a cow more? Now, the very exciting part of it is that it will shock you, but we might, if there is time, if we can build a model like that, right? Where we expect the bad output and intuitively follow our minds through what the models do. You would realize that if we pass a brown car, okay, or a car with more like tiger light colors to this model, it might tell you that it's a tiger. Or if you pass any car that looks like a black cow or anything like that, it will tell you that it's an elephant. Why? Because it only knows elephant and tiger and nothing else. But the item that you've passed to it looks closer to an elephant than it is to a tiger based on the features in the very image you are presenting to it. And in that sense, the image is black. And if it's black, between this and this is darker. Okay, so it's pattern recognition that we are doing here. Okay, what in technical science we will call as feature learning or feature extraction. It takes some specific parts of the data you give it, and it makes sure that it learns them very well. Okay, so that when new data comes in, it also looks at the new data, extracts all these features that it gets from it, and then do some comparison with what it has learned already and then what you are giving to it. And the one that is very close is what it assumes to be the model in this case. Okay, that is classification for you. That is what we call as a classifier. So we will build models that are classifiers in this class as well. Now, on the other hand, apart from a classifier, we also have something called a regression. Okay, so if we are talking about supervised learning, we have a classifier, we have a regressor, or yeah. So just like the way classification was called classifier in the sense of when you are building a model, with regression too, we do have what we call as regressors. Now, the regression case is simple. I've already mentioned it. Now, a typical example is if you want to predict something that is in a very wide range of values. Okay, I mentioned an example to be sensor data. I mentioned an example as time being quantitative because it takes on lots of values. Microseconds can come in lots and lots of values, right? That is regression. That is what regression seeks to solve. And so a typical example that you see in the image right here is trying to estimate, okay, what the price of this apartment is, or what the price of this house is. So all you need to do is to get data, and the data should describe the type of model you want to build. In classification, we saw that the type of data we use for classification has to be distinct, means that it has to be finite. But then in regression, the type of data doesn't necessarily have to be finite. You don't even know or do some data. Sometimes you don't even know the ranges that are possible in that very data. It can be anything. So even if you understand that the data ends at 100 and starts from 1, you don't know the possibility of having a 99.999 and it's not being 100 even. An example is exam scores. Mostly, right? I think exam scores can be thought of as distinct or even not distinct. Let's look at it in the sense that it's not distinct, because typically somebody can get 99.5, somebody can get 75.5. If it's marked correctly, someone should even get 73.3. Okay, that is based on the type of marks that the lecturer gives for each question. And you can understand that anything at all is expected. And so your range is not predictable. That's what regression seeks to solve. So you can use regression to solve more use cases like what I just mentioned. So predict the marks of a person, right? So you look at your classroom, you take data from the individual students in your class, and then you build a model to be able to predict the score, average score of a class, okay, or to be able to predict the score of a person, or to predict what you say that maybe this year you estimate that this class is going to, score this or this. So the scores are basically going to come in a very wide range, and your model is supposed to learn on history based on the marks from that very class from the past. So using the past to basically predict the future. And this past is supposed to be numerical, very numerical. Okay, that is what regression problem seeks to solve. Right? So with what we've written here, of course, is basically what I've explained, that if possible output values of the function are continuous real values, then it is called regression. Okay, continuous real values. So two types of supervised learning models, okay, or supervised learning algorithms. We have regression, and then we have classification. Use regression if you know that your input or your training data or what you want to predict or classify. No. Use classification. I don't want to spoil it. Use classification if you know that what you are dealing with has a definite structure. You understand? So if it's definite, then you need classification because you know where it ends and then where it starts. Okay. Example, if you are predicting whether it's a yes or a no answer, okay, or if you are training a model to determine whether something is a yes or a no, that is classification. Okay. Or if you are training a model to tell you the marks of a person, but then this marks has been determined already to range from 1 to 10, then you know that it's definite. So you need 1 to 10 and no decimal intervals. Then it's classification. That is total classification. Okay, so you expect 1, 2, 3, 4, 5 to 10 at the outputs, and the model won't go beyond 10 or won't give you something like 9.5. This is classification. Now on the regression side, use regression when you know that your output is non-deterministic, meaning that you don't know the output whatsoever. It can range from any value to any value, or even if the range is determined, the individual items within the range can be anything. So you give it data between 1 to what's not, or data that you don't even know its beginning to whatever end. And then you expect that next time when you ask your right questions, it should just give you the prediction that is supposed to be a number. All right, that is regression. Now, with supervised, right? With supervised, we learned in one of the slides that we've done already that the data output has to be there. Right, so you get this image.
Michael, there's a question. There's a question that can we use classification when the input is binary and regression when the output is non-binary?
Yes. No. Yes,
What I
and
think
no.
you should do is that if you can go through the regression and that explanation you just gave, if you can go through that side.
Okay, sure. All right then. Speaking of binary, so what do we call as binary in the first place? Give me a moment. All right. So if it is a yes, if it's a yes or no, you are correct to say that you are. But binary, dealing with two things, it's not necessarily, if you say non-binary, it's not necessarily regression. Okay, because if we are looking at a range of 5 items, it's not binary. That's not binary. Okay, that's not binary, but that is distinct. So I wouldn't want you to say binary. I would want you to use the word distinct. Okay, categorical values, and numerical values. So we do have that those terms, categorical values and then numerical values. Categorical values are categories of items. And these categories include binary, which is very correct. So you can use binary for classification, but non-binaries are still categorical values. And non-binaries include an example like 1 to 5, 1 to 10. They are non-binary, right? But then they are still what? They are still categories. The trick is that their start and end has to be determined or known. The range, you understand? The range is known. You know that it's finite. That's exactly it. All right. I think a trick to catch this thing better is if you go back to learning about quantitative and then qualitative data. That's the whole understanding of this type of data is the same way that you can transfer the knowledge into how or data to expect for classification and data to expect for regression. All right, so for regression, it's not binary, which of course you are correct. Binary can never come to regression. That is true. But again, non-binary, yeah, so non-binary data, we still have types of non-binary that do not come here. Exactly. So it can be non-binary and the start and end are deterministic, or the range is very known. It still goes to regression and not, it still goes to classification and not regression. Regression only comes through when it's very, very common. I think I have a graph to show. I want to show you a graph if possible. Okay. We can't get a graph, but we can get this data. Now look at this data. What's happening here? Okay. All right, I couldn't find it, but this data, unemployed, right? If you look at this very column we have here, this is numerical. This is for regression problem. Why? Because we have 235.6. We have 232.5. You can see that it's non-deterministic. Like anything at all can come from here. Anything at all. Anything, and I mean anything, any number at all can come from this range. So we don't know anything. So you can, even though it starts from 235.6, you realize that here it just switched to a very low value, right? Which is 232. So you expect that the values can take on any continuous range. You understand? But for classification or for categorical values, you'd expect this to be grouped. So categorical values are basically grouped. I think that's the right term to use. They are grouped. Can be yes or no. It can be, I think when we are taking data, we say that you agree, you don't agree, you somewhat agree. Okay, so we call that like a scale or something like that. That's an example of categorical data. When we take this type of data, we are basically taking categorical data. You strongly agree, you disagree, you are neutral, you agree, or you strongly agree. This is strongly disagree, sorry, or you strongly agree. So we know that the ranges are determined, and whoever will fill this form is not expected to add in any value at all apart from what has been put here. That's because we know the range, or we know the type of values we are dealing with. That is what categories are, and that is what a classifier is meant to work on. I believe this should be clear. Yeah, I believe this should be clear. I'm sure it's clear. All right, then. So we go back to why we went back, the unsupervised learning approach. Now, with unsupervised learning, the difference between this and the supervised is that for unsupervised, we do not know what we are learning in the first place. That's why we call it unsupervised. So we do not know the labels or the ground truth values. What we call as ground truth is the outcome that we already know of, right? So we don't know it upfront. So we give it a car, but then this isn't there, this isn't there, this isn't there.
So you can wait for extra 2 minutes. You can while you get yourself ready. Yeah.
All set. All right. Okay. So for supervised, when you give it data, the data is labeled. So for this data, we know that it's a car. Okay, this data to be understood that it was a car. So all those descriptions or the associated values from history are there for our model. But we don't supervise, we don't know. We basically have data, and then we know the type of data that we want information out of. So this is our data, but then it is not example, or typical example of what a supervised algorithm does is clustering. So we saw that we have classification, and then we have what do you call it? We have regression in supervised learning. Now, supervised. So what is clustering? Because we don't know what exactly this and this are forefront, the model now groups what is similar in one place and groups what is dissimilar in another place. Okay, so here it finds that this and this do kind of look alike. Why? Because it looks like they all have light, even though this one looks like an eye, it's still very significant. They all do have something like glass in front here and the side. This one also has the same thing and it's the same number. They have doors. They do have wheels under them. So this and this look very much alike. So if they look alike, then it means that they all belong to the same family. Then this two and this two, it looks like they are alike. And so, yeah, why? Because, I mean, they are all motorbikes, human-wise, that's what you say, but machine doesn't understand it that way. It's basically looking at what and what I hear that are alike. So it does the comparison for all of them. It can take this bike and then take this car and then look at their similarities. Now, if the similarity is very large, okay, if it finds that, let me not use very large, that is mathematical, but if we find that the similarity is not there, okay, they don't really look alike. Because if you look at this and this, they don't look alike, then it means that they don't belong to the same group. So it creates another group for this one alone and this one alone. Now it goes again in the next iteration to look at this and then compares to this. Does this look like this? Or does this look like it belongs to this group? Now it realizes, no, this looks like this more than it looks like this. So it puts this in this group. And that is how it goes about it until it separates this and this. And that is the clusters, what we call as clustering. You understand? It's pretty simple. It's very simple. It's very, very simple. So the task is to identify the patterns, like group the similar objects together. You understand? So just like we had different types of unsupervised, of course, I've mentioned that supervised. I've mentioned that unsupervised also have types. And then this part of it is also association rules, right? And unlike clustering, association rules are also there. And this type of models basically relate what we have to what we don't have. Simple. So you have a car in your data set, it's still unlabeled. You have a car, you have you have this car, this type of car, and then you have this type of car. Now you have this and then you have this. Now, what do you think this will be most likely related to or associated to? What do you think this will be most likely associated to? So it looks like two items that are coming through. This one is more likely to relate to this than it is to this. I mean, what would somebody be in the car and then wear a helmet for? You understand? Unless, of course, specific, what do you call it, cases. So that type of those type of models are also there. So more examples of unsupervised is what we see here. We are able to group different types of people. So these are more like dummy data of individuals, but then they all have different colors. So you wouldn't put red at where yellow is. You wouldn't put mauve or violet at where green is. So we are able to group them, but then we are not able to tell that this is a yellow person. See, there's no label here. That is what we mean as no label. We can't say that this is yellow. We can't emphatically say that this is green or this is mauve. It doesn't have that data. That data is only present if you are dealing with a supervised learning approach. Unsupervised, you don't know it. You don't. And so all the model tries to do is to group things that are similar to each other and then leave them as they are. Okay, that's the understanding. So it's able to create a cluster. And in that sense, we call it a cluster. So it created a cluster, these people, and then all of them are very similar. So they carry the same traits. That's the fact that they are blue. These people too are very similar and what's not. And out of all this data that we gave it, it was able to find 5 groups of 5 clusters. And that's what is important. So how does it now make a decision? It means that whenever new data comes through, all what it's supposed to do is to basically look at the new data and then look at the clusters that it's having. Compare the new data with the cluster to identify whether it looks similar to this cluster or it looks similar to this cluster. And if it does look like this cluster, basically tells you that, yes, this is the cluster that it falls on. You can intuitively or when you are programmatically define the names of each of your clusters. Okay, now you know that I have 5 clusters, but then this cluster is called this cluster is called this. So whenever your new data comes in, it will tell you that this falls under this very cluster. That's clear? Anyone with questions? Before we move on to another type.
Okay, what if a new data is input into it and it doesn't fall under any of the clusters? Is it going to create a new cluster for it, or is it going to associate it with any of the clusters over there?
Great question. Great question. Anyone else? It's good. Okay, let me answer this, and if anyone else also has some, then we take it. Right. So if the data is not related to any cluster, what is it going to do? Now, just like what we saw with the classification in supervised, there wouldn't be a situation where the data doesn't fall in any cluster. True, the data doesn't fall in any cluster, but it will still choose a cluster for you. Why? Because it's looking at certain features that you may not even look at. So here we see that we have blue, we have violet, we have green. Give it an example like brown. Okay, we don't have brown here, but we do have red here, we have yellow here. This type of yellow that we have looks more like brown than it does to red. So the difference between this red and then the brown are going to be better than the difference between this blue and the brown. And also for the mauve or violet and green, relating these three to the brown wouldn't work that much, but you get some very good results from red and then yellow. But going deep down to select one, it will choose yellow. I'm saying that because I see that this yellow is close to brown than red is to brown, right? So even though we don't have brown here, you might get a cluster to be this very cluster. So regardless, you still get something. Okay, you will still get something to work with. So that is how it works. If you want to, again, this is where it gets very tricky. The clusters or the number of clusters that it determines, right? If we are going technically, sometimes if the clusters that you are supposed to expect are the output to the model. So we have ways of, and it's not a one-time process. You do not give it once. Sometimes it's basically coming off of technical experience. You already know that this particular data, even though I don't know the associated labels to them, I'm expecting that they should be grouped into 3, okay? Or they should be grouped into 2. So you give this number to it, and then it tries to group it into 2. Sometimes even if you test, your group of 2 may not be effective unless you increase the number or you tweak it. It's something that we tweak until we get the perfect accuracy. Now, after that, what is happening inside the model is that it has divided your data set. It has been able to create clusters based on what you give it. Now, with all these clusters that it's having, it's waiting for you to give it any sample data. And because it has already learned that it's having 5 clusters, all these 5 clusters have qualities that the model has learned. So you can see that each one of these have qualities, right? This is blue, there are qualities to blue. This is green, there are qualities to green. So anytime you feed a new model, it's basically looking at the qualities of, sorry, not a new model, a new data for prediction. It's basically looking at the qualities of the new data compared to each one of these clusters. So if it's brown, like the example I gave, then it has to compare the qualities of a brown color to all of these. So even though brown wasn't in the data set, it's closer to being yellow than it is to being any one of these, what you call it, clusters. And so it will tell you it belongs to this very cluster. Do you get it?
Yes, please. Yeah,
beautiful.
that answers it. Thank you.
Beautiful. All right then. Okay. So we can also explain this with a question you raised. I'll try and explain it with YouTube. Okay, that case study can be explained in so many ways. So we do have algorithms. So type of those that are able to answer questions like customers who viewed this item also viewed that item. So you can go to Amazon, right? Or no, let's take to YouTube. You go to YouTube and you search for football videos. As you're scrolling through the list of videos that are basically football matches and watching them, you do realize that sometimes your endless scroll gets filled with football videos. TikTok, as an example, the moment you start liking and then paying attention to some specific niche or something, if it's related to football, you watch one video from content creator that is football, you open another content and it's football. It's football. It learns. Next, before you realize your FYP or your For You page gets filled with football matches. Now, how is that happening? Okay. How is that happening? So it has understood that that is what you want to learn. So it's now looking at what you have learned to find that group of items that look like what you have learned. You get it? So it finds out that even though you've watched videos of Messi, it's the same football. And so if it goes through the database it's having, comparing all the types of videos that it has, it will notice that Ronaldo videos are closer to Messi's videos because they all have specific features, right? They are all football. And so it will start recommending you videos of football matches, which Ronaldo will be inclusive, and Messi will also be inclusive because they are likened or they belong to the same cluster. It will stop showing you videos of acrobato or something like that. You get it? It knows that you viewed Messi and then you are likely to also view Ronaldo. Unsupervised learning. Do you understand? I think that was good. Right. Now to the last one. And a very tricky one, reinforcement learning. Right. If you paid attention very well, right? If you paid attention, you realize that all these approaches I've mentioned, supervised, unsupervised, and now we are coming to reinforcement. With the two we've learned so far, you realize that it's basically more like our day-to-day life activity, how we as humans learn stuff. The supervised is when you already know the answers already with history. So you have history and then the answers to history. You get it? You already know that 1 + 1 is 2, 1 + 2 is 3, 1 3 is 4. And then now you're asking a question of 1 + 5, and then you want to answer this question. So you go and look at the patterns that you've already seen from 1 + 1, 2 plus all those ones, and then see what's coming next. Okay, it's the same thing, more like a multiplication table, 2, 2, 4, and all those things. So you look at if you have 2 by 2 up to 10, then you realize that the next one that should follow should be incremented by 2. Why? Because you have already seen in the past that all the answers that are following are of differences of 2. That is supervised. Now, supervised, you don't know yet, but then you find out that if you group this item together, they have specific qualities that are very unique to them. And then this group also has specific qualities. So you group stuffs based on their likeness. That is unsupervised. Now with the learning. Oh. Okay, can we mute him?
Yeah, Michael, I have done that.
All right, so reinforcement learning is pretty simple. Now we are dealing with two entities here, what we call as an agent and then what we call as an environment. Okay. Now the agent here is basically what you are trying to train, and the environment is the specific data or what you are trying to let the agent understand. Now reinforcement learning is quite exciting because then you don't need to get all the answers forefront. Unlike supervised, where you need to get the answers forefront or get history, incomplete history, and unsupervised, where you don't even need answers to history at all. Unsupervised, you can get small answers and you can also not get answers. That is fine. So that is basically what we do. A perfect example of what a supervised, a reinforcement learning is, reinforcement learning actually. So what it is that this agent is basically going to ask questions, or you're going to ask questions to the agent, or what you call as actions. So it performs actions, and then the environment or you are able to determine whether what answers they are given is right or wrong. So we deal with two things here. We deal with rewards and then feedback. Now pay attention. It's more like you having a baby. Okay. And then this baby, they do good and then they do bad. It's like training a baby. So sometimes they don't know what is good and bad. But then how do they know that something is bad? Unless you apply correction. Okay. And then how do they know that something is good? Unless you reward them. That is when they know that something is good. So if they do something and it's nice, you clap for them, you are making merry with them or something like that. That is the rewards. And that is the feedback that goes into them. So they get to understand that what they did is good. They learn and then they keep it. Now, what happens if they do something bad?
Yeah,
Question?
that's a chip in it. I think that is how those who train dogs, that is the approach they normally use. So when you teach the dog how to maybe jump or maybe greet or all those things, they will use maybe some food and they will try to guide the dog to do it. When the dog is able to do it, they will give them the food. When it's not, they are not able to do that, they will just kind of punish, like take the food from them, right? So in doing that, the dog, okay, anytime I do this, I'll get reward. So I'll go at it. So it just coming like that is what they do. So basically they are using reinforcement learning to train dogs. Interesting. Okay, go ahead.
That's exactly it. That's exactly it. So dogs or babies the same way, right? So this slide is literally using a dog as an example. So dogs do not know anything, just like Norbert explained, right? But then what you do to it, okay, if it does something right, if you are teaching it something and then it gets it right, Then you reward it. You give it something, put food there, and then it will know that what it did was right or it got it right. Okay, clap or something, and it knows that it's right. Now, if it gets something wrong, the train when they get something right, you are going to punish it somehow. But the feedback you give to it, okay, determines if it learns that it did the right thing or not. That is reinforcement learning. So this one is a bit quite different and a little challenging than the others because sometimes the feedbacks are not given right when the actions come through. Okay, so the feedback can come in or the rewards can come in at any time. And then there is a mechanism that you need to devise for it to understand that it was based on this action that I'm getting this feedback from you. So it's quite tricky, but then it's very, very clean and it's very applicable to lots of situations. You will see this one in robotics. You will see it for robotics. It's almost everywhere because that is how robots are trained. They learn on very, very dynamic data. So you sometimes don't have the answers to everything. Okay, ChatGPT currently is even training based on this understanding. If I'm to give an example, you do realize that we get a situation where you are able to ask it a question. Now it fails, you continue to ask it, and then you get in the future, you're able to tune based on the correct answers that you ask it, you tell it to use. So imagine you going like, is this the answer to this? And it's like, no. But then you know that that is the answer. So you go ahead and prompt until later on you are like, this is actually the answer. Then it will be like, oh, so things like that. There are technicalities to it, but that is a very basic example. Or when you are on a particular platform and then they ask you if what you are seeing is right or wrong. I think also on TikTok, you would notice that. So if what you are seeing is relevant to you, then you go ahead to select yes. It means that you've given some form of feedback, right? And that feedback goes back into that model that recommended that video to you as a reward. And so the model now enjoys the fact that yes, it made the right decision and it will come back with more. But then if you answered with no, then it's not going to come back with more. It may not be right on spot, but later on that data also goes into the model again. And then now it's able to understand that, no, this video that I showed you didn't get a right feedback, so I'm not bringing it again. Reinforcement learning. You understand? So this is the baby example I was talking about. If the baby gets the fact that this is a glass, correct? Okay. No, sorry. So the task is for you to basically tell us what this is, right? Or something of that sort. I think I'm in the clear picture here. But if whatever it got or whatever you're trying to ask it is correct, then you have something to reward it with. So the reward can be anything. Feed it a baby bottle with milk inside and it's enjoying the milk and knows that it has done the right thing. If it didn't get it right, then you can penalize it. So that punishment is a very significant part of it. If you don't apply the punishment, it doesn't come. Okay. So it doesn't actually learn that what it did is wrong. So there are two things to it, reward and then punishment in unsupervised learning. And that is how we tune the model to do the right thing. Okay, questions on this one? Questions? Right. Any question?
What be that? No, no, media.
Are you asking a question?
Yeah, I have a question.
Great.
Okay, so you know that with babies, like when they do something, you can beat them, you can take something away from them. But with the AIs, how do we punish them? How do we do that?
Yeah, so that again is very technical. Now the punishments can be mathematical, right? It's mathematical. So it goes into the model, but then it's what we call as a loss. Okay, it's a loss. So we then direct it on the fact that this is a loss. And so because of that, you are not getting this, but then it's mathematical. And I think we'll look at that if time permits. But then what we understand theoretically that is that particular part of it is what we call what do you call it, reward, or that particular part of what we feed into it is what we call as punishment. Okay, so math does a lot of things, surprisingly. You get it?
Yeah, I'm okay.
Exactly. But they are feedbacks. So we call those two feedbacks. So the feedback can come in two forms. The feedback can either be a reward or a punishment. So you direct a reward feedback to the model if you feel like the output that it gave is correct, or you direct a punishment feedback if you feel that it's basically a mathematical signal. And we'll look at all those ones as well. All right, any more questions? Mm-hmm. Okay. Then I think this ends it for us right now. So we've learned a lot of things. So the very essential part of this is us getting a grasp of what machine learning is. And we've talked about the fact that it's basically a field in computer science, right? That is using history or past data to make computers learn and make decisions on the current and even the future as well. And then how we do that is based on certain paradigms, okay? And these paradigms include a supervised approach, it includes an unsupervised approach, it includes a reinforcement approach. And we've looked at each one of them and how they learn. And so what you are supposed to right now understand before even moving on is that now you have three. And so each one of them, you would have to better understand the type of data that they are required in order for you to achieve that. So for supervised, what type of data do you require before you can get a supervised model? Okay. And even the supervised model that you want to build, what type of model are you building out of it? So you can get a regression model, you can get a classification model. If you are dealing with a classification model, then what type of data? It means your data has to be quantitative, or your data has to be categorical. It has to have finite, data samples in it. It has to be deterministic. Those type of data are for models that are meant to be classifiers. For models that are meant to be regressors, the data should take in continuous range. Example of such data can be sensor data. You understand? Any numerical data at all is data that we use for modeling regressors. So example of regression models are models that we say that, and as an instance, we are building a model to predict house prices. Okay, house prices can be any value. A house can range from basically 0 Ghana cedis if it's free to what's not. You don't even know. It can be any value. So that's a good example. If you want to count stones at a particular area, it can be any value. So all these things, all these type of examples are what regressors pay attention to. If you don't have the answers to history forefront, okay, then you have to look at two things. So you ask yourself two questions. Is it that I have answers to history, but they are not enough? Or is it that I don't have answers to history at all? The first case, if you don't have answers to history at all, but then you have data and you want the answers, then you go in for unsupervised learning because you don't have the answers to history. So a model now learns on your data to group them for you. And that approach is what we call as clustering, right? So it looks at the data and it's able to tell that this data, this part of the data, or these very entities that you've presented to me that are part of your data look like they are similar. And so let's put them in this cluster. It names the cluster and then it looks at some other data too that are similar. So it groups all the similar components in the data together. And then next time when you ask the question that what type of data is this or what cluster does this data fall under, is going to be able to tell you the very cluster that it falls under, right? Now, if you have okay, or if you have history and you have very small, what do you call it, answers to history. Okay, some history you don't have answers to them, but you do have very small. Then you can go in for reinforcement learning. So you start small, you start with a smaller number or even, and then you show a model that this, or what does this represent? Or you teach it that this represents a cat. Okay, it learns it. Then later on, you show an example, which you've not given it. So what is this? Then you show it a bottle. Now it's not able to tell that this is a bottle, and so it gets it wrong. Then you send in what we call as a punishment. And that punishment, you also add the label to it and say that this is a bottle. Now it comes back again, and it understands next time that this is a bottle because the punishment, I mean, was penalization. So it gets to understand that this is a bottle until you show it different things. So it's a very dynamic setting. It's reinforcement learning. It's a very, very dynamic setting. The limitation is basically what you have not punished it to learn from. That's the limitation. So if you want it to be exposed, if you want a very deep understanding of reinforcement learning, start watching videos on robotics. That's exactly how they are trained. So if you want a robot to move or walk, right? Boston Dynamics, I think, has a very good documentary on how they train their robot dogs, how they take them from not knowing how to walk at all to directing them on how to walk and even dance and even stand on two legs. It's all directions. And that's algorithm that is working in the basically reinforcement learning, right? So these are the three paradigms of machine learning that we've looked at. And I hope that this will benefit you as well. Do you have questions?
Yes, I have another question.
Go ahead.
So with the classifiers, when you were talking about them, you were saying like binary. But then the Likert skill you showed had 5 options there. So does the classifiers actually work with only binary, like yes and no, true and false?
Binary data, yes, is for classification, strictly. But in classification about binary data, it's just an example of the type that should work with classification models. Likert skill ranges, it can range from anything. You can choose anything as Likert skill, but it's definite. Whatever you choose as the term Likert skill has to be definite. It means with which you are choosing from. It can be 5. So I showed an example here where we have strongly disagree, and whatnot. But this one aren't numerical. And then we know any user that is filling this form has to choose one of it. So if you are building a model, you will build a model to predict one of these. It can't predict anything outside of this skill or anything out of the values that we have here. This is what classification is about. So it's not just about binary, because as we can see, this isn't binary. You understand? So it can even be 1 to 1,000. Yes, be careful. It's quite tricky. The fact that 1,000 doesn't mean that it's strictly regression. No, or it's strictly classification. If it's 1 to 1,000 and the values within 1 to 1,000 are not deterministic, it means that you don't know if you can get 999.5. That one you don't know, right? It means that that's fit to be a regression. But if you know that 1 to 1,000 and it's supposed to count with one step as you move forward, like 1, 2, 3 to 1,000, it's still definitely you have values to choose from. Then it's classification. Even though you have that huge number, it's still classification. So that's how to understand it, right? As long as you know the definite points to choose from, it's basically about choices. Then it becomes classification. But if you don't know what to expect within that particular range, it's numerical. And that faces to be a problem. You get it?
Yes, thank you.
You're so welcome. All right, then. More questions? Okay. So this was just a brief intro. I think next time we will do the installations, the necessary installations that we are supposed to do. And then if time permits, next time, which is tomorrow, we do have to get our hands dirty, start from there.
Yeah,
Right.
so Michael, on that bit, I would suggest we go with Google Colab, right?
Okay.
Yeah, I suggest we go with that so that we don't need to do any physical installation, blah blah blah, right? Just kickstart. But of course, you can have a session with them going through how you can install them on your. On our practical session, I would love for us to go with Google Colab. I don't know what you.
Yeah, it saves a lot of time. So I think after the whole training, then we can look at what other things like next step to it.
And you can start with taking them through how to set up their local environment on their machine. But on your training, let's use Google Colab. I will create a shared drive that everything you do will be saved in there, right? So that they can have access to it during the training session.
Beautiful.
All right.
That's good. Right. Okay. Sure. All right. No